Snow webinar. But before I do that, I'd like to provide you some background on the Colorado River District. The River District for more than 80 years has served as the primary water planning and policy agency for the 15 counties on the western slope that make up the main stem of the Colorado River and its tributaries. The Colorado River District is a small, special governmental entity with no regulatory authority, funded almost exclusively by property tax. We don't ask a lot. The average homeowner in our district pays just under $8 annually to support our work. So if you own property on the western slope, thank you for supporting us. Our presence is essential to ensuring a secure water future for the western slope. In 1937, we were founded out of conflict and in direct response to Trans Mountain diversions, taking more and more west slope water to the Front Range. Today, that is still at the core of what we do, but it's so much more. We're representing agricultural, recreational, and environmental needs for west slope water. At a time of increasing unpredictability and rising temperatures, the Colorado River District continues fighting to protect west slope water by planning for a hotter future that will impact our precious snowpack and inevitably our water supplies. In today's Know Your Snow webinar, we will have presentations by Dave Kanzer and Dr. Jeffrey Deems that will highlight the importance of snowpack and the latest associated science that help us understand and quantify our water supplies on Colorado's western slope. They will also discuss the state of the science of our snow hydrology and its impact upon our water supplies in the face of our warming climate. Now, as Deputy Chief Engineer at the Colorado River District, Dave Kanzer, or DK as most of us call him, has been working on the complex web of water quality and quantity issues facing the Colorado River Basin for 25 years. Along with the Colorado River District team, DK is implementing a variety of projects and programs to help address growing demands and dwindling supplies. In addition to developing and implementing water use efficiency projects, DK works to understand the hydroclimatic drivers that affect critical snowpack accumulation that determines the seasonal water supply availability. Since 2016, he has been managing a regional cooperative cloud seeding program to help increase water supply availability for multiple beneficiaries, including agricultural, municipal, environmental, and recreational interests. Dr. Jeffrey Deems is a research scientist at the National Snow and Ice Data Center and the NOAA Western Water Assessment at the University of Colorado. His research centers on spatial and temporal variability of seasonal mountain snowpacks with applications in avalanche prediction and water supply management. Dr. Deems is also a co-founder of Airborne Snow Observatories, Inc., which is building on a 7-year legacy with NASA Jet Propulsion Lab to provide snow water data products for operational decision support in mountain watersheds worldwide. Without further ado, here are Dave Kanzer and Dr. Jeffrey Deems.
Well, hey, good afternoon. Thank you so much for that great introduction, Alicia. I am so happy and honored to be here, especially with my friend and colleague, Jeff Deems, to talk about one of my favorite topics, snow, well, several topics really, snow, water, mountains, and rivers. So let's get into it. Why is snow so important? Maybe an obvious question to many of us, but really it's an overwhelming majority of our water supply. It's responsible for what flows in our rivers. So what falls from the sky, accumulates in the mountains, of course, is the main resource that we curate and manage here at the Colorado River District. This white reservoir, we like to call it, feeds and preserves our water supply throughout the year. For 40 million people, it is absolutely essential. It strongly impacts and determines whether there's an imbalance between supply and demand in the Colorado River Basin. It boosts our recreational economy. I don't know about you, but I'm a big skier and boater. I really enjoy the snow that it brings throughout the ski season and provides that whitewater experience. However, we are faced with climate change, and climate change is snow change. So where are we today in our look at our snowpack and our resources as we look forward this year? This map that you see is a common image that many of us rely upon, but there's a whole lot behind this map. There's a whole lot of detail that has brought us to this point and will determine our future. In fact, this year, as we look back, it started out extremely cold. We're setting records in October. You may not remember that or appreciate that because January was a record warm month. Across the globe, we set records for the warmest January ever. And in Colorado, we're still in the midst of drought as defined by the U.S. Drought Monitor. If you look at this map, the majority of the state is either abnormally dry in the yellow or even in experiencing severe drought in corners of the state in orange. So where does that leave us? Well, excuse me, I forgot to point out that in contrast, in February, Breckenridge experienced its snowiest month, February, ever. And so that's in direct contrast to that drought. So as I started to say, where does that leave us? It leaves us with a whole lot of questions about our future. How do we possibly predict our future, our water supply, when we're faced with such crazy variability throughout and conditions that are no longer like what we have, our instrumental record has shown us. And Jeff will go through that with us. But, and scientists like Jeff have been extremely active trying to address some of these questions and help us reduce our uncertainty. How are they doing this? Well, basically putting together more accurate data sets, more representative data sets of today's conditions. We're doing this through intensive monitoring and assessment, and we're connecting those research products with operational. Our operational decision-making relies heavily on this new research. So we're really boosting that collaboration and coordination. And in fact, at the same time, we're trying to figure out how to mitigate and adapt to a changing world. We're doing this through cloud seeding and implementing these programs throughout Western Colorado. In fact, this is going on throughout the West and through the world. And to do this, we need a stable, long-term funding stream, and we're working on that here at Colorado River District, along with our partners throughout the basin. So how does the water hit the ditch? Where does the rubber hit the road here in the Colorado River Basin? The Colorado River Basin is a story of one of the hardest working rivers in the world. And many of you know this and live this year in, year out. But our natural basin, as defined in black, is broken up into the upper basin and the lower basin. We have tributaries and high mountain areas, our catchments, that feed uses throughout 7 basin states and areas outside of the basin in these hatch areas. The story again is a complicated one, and one which involves not only 7 basin states, but 10 autonomous sovereign nations or Native American tribes and 2 countries. It's a story of supply and demand. In the upper basin, over 90% of the water arises, but it has to be served almost 90% of people in the lower basin. So we have a plumbing system and a system of storage and delivery that is set up to do so, and hopefully in a secure way without shortage. And that's a huge challenge today. To do this, we really have to understand where the water is, where the snow is. And this map, I think, really shows the picture. And if there's one thing you take away from today, is that we have a very small area that is catching that snow. And luckily it's oriented in a way that captures a lot of the snow, of the precipitation and moist air masses that come in. We're going to talk about that. But that has to feed all the red areas and the large cities and deserts in between the headwaters and the mouth of the river. So when we drill down and we look at this image, courtesy of the Colorado River District, it really brings into focus, if you will, that thin ribbon of territory above what our target area is about 8,500 feet, where the bulk of the snow falls. About 85% of our water is derived, over 15% of the landmass of the upper Colorado River Basin. And that's shown in this table, again, courtesy of Don Meyer, who put this together, of our staff, the Colorado River District. If you look at those lands above 8,500 feet, it constitutes, again, about that 15%, a very small amount of acreage. The majority of the lands are in the valleys, thirsty areas that rely on those water supplies. And just another look, I think, of the Colorado River District, about a third of the state that is responsible. If you look at the inflow of Lake Powell, these lands provide about 73/4 of the water that flows into Lake Powell downstream comes from the Colorado River District.
Well, in addition to that small amount of area generating the bulk of the stream flow for the Colorado River District and Colorado River broadly, that small area is uniquely susceptible to changes in our climate, and these changes we are seeing. This map shows the change in average annual temperatures from 1895 through 2018 in Colorado River District, and we're seeing changes on the order of 4 to 5 degrees in parts of the district. In reality, this is just a slice out of this big warming bullseye that is hitting the upper Colorado Basin over that time period. And this is a problem for us because we rely on the snowpack. And that's because warming reduces stream flow through a number of different mechanisms in this snowmelt dominated basin. Firstly, in the fall and spring, those shoulder seasons where snowfall is occurring at warmer temperatures, with just a little bit of warming, that snow instead falls as rain. And rain will either soak in or run off immediately and doesn't add to that white reservoir that can persist later into the drier months. Earlier snow melt in the spring from warming or from dust on snow, which is connected to regional warming as well, produces a less efficient runoff. So it's less water delivery to the stream network and our reservoirs. Partly that's due to greater water losses to the atmosphere under a warmer atmosphere. A warmer snowpack, warmer snow temperatures increase sublimation losses. That's direct change from solid ice in the snowpack to water vapor in the air. A longer snow-free season due to a later start to the snow season and an earlier end to it means that that snow-free ground can evaporate more water than it would when it's covered by snow. And a longer growing season means that plants and forests have a longer time to take water up out of the soil and transpire it through their respiration process and lose that water to the atmosphere. All of these and other factors combine to produce what we term a climate sensitivity of annual runoff in the Colorado River Basin. And we see that as about 3 to 4% decline in annual runoff in the basin for every 1 degree Fahrenheit of warming of the atmosphere. Just to put that in perspective, 3 to 4% is on the order of double what Las Vegas is allocated per year and close to 18 months of supply for the city of Los Angeles. So that's a big factor, and we're seeing in parts of the basin 4 times that amount more. So certainly cause for concern and a better understanding of not only what's causing it, but what we can do to mitigate and adapt to it. Really what we're talking about is a global cycle influenced by the warming of the atmosphere as well as more local processes. But we're concerned with this one component of the global water cycle where we have a seasonal storage of water in the form of ice and snow in our mountain basins. In the springtime, that snow melt running off into streams governed by its infiltration interactions with the soil and groundwater systems to connect to our stream and water delivery networks. To keep tabs on that seasonal storage of snow, we've developed over quite some time an operational snow monitoring network to measure, and the property of interest is the snow water equivalent, or SWE. And that's the amount of water that you would have if you melted down snowpack at a given location. The cartoon at the upper right tries to illustrate this a little bit. Typical new snow density is somewhere in the order of 5 to 10% water, the rest being air. So the super fluffy snow that skiers really like is 5% or even less sometimes. So if you have 12 inches of, say, 8% density snow, that's going to melt down to an inch of water equivalent. If we double that density, either a heavy storm comes in or maybe the new snow's been sitting around for a few days, that density increases to, say, 16%. That gives us 2 inches of water for every foot of snow. If we move into the spring, those densities climb up to 40 or 50%. So close to half water, which of course would give you 6 inches for every 12 inches of snowpack. So we measure this water equivalent a couple different ways. One is manual, and this technique was invented around 1910, and it's still used operationally today. This federal sampler takes a core sample out of the snowpack and then is weighed out in units of inches of water. And then a similar measurement is made automatically at the SNOTEL stations, or snow telemetry network. They use what's called a snow pillow that weighs the snowpack sitting on top of it, again, reading out in units of water. The SNOTEL network has been built out to over 800 stations in the western US, which at this broad scale map looking at the whole western US looks like a lot of stations, but as we zoom into individual river basins, frequently there's one or even no stations in your basin of interest. So the distribution of this network is actually quite sparse at the watershed level. So really what we're trying to measure and keep a close eye on is the seasonal evolution of the snowpack at these stations. And that's represented by this orange line on the graph here, showing the accumulation season and melt season, accumulation of water equivalent over the period from the late fall into the late spring. In this particular instance, the snowpack neatly behaves in this defined accumulation and melt season. In other stations at, say, lower altitude or in drier environments, you may have a more intermittent snowpack with SWE curve hitting the zero mark several times during the cold season. Nevertheless, this median or average behavior for the accumulation melt season expresses itself differently depending on how the year evolves. In this case, with the blue line, the water equivalent was pretty closely following the median curve until about mid-February, and then a strong ramp up in several intense snowstorms put us well above median that particular year. We can also see, of course, that in the middle of the melt season, there's a couple of sizable snowfalls that added some mass to the snowpack and delayed the melt out into late June in this case. So that's snow water equivalent evolution over the time series of a water year. There's other things going on and that's the partitioning of that water equivalent into snow depth and snow density, as I talked about a moment ago. And I'll draw your eye to the fact that in this case, snow depth peaks before the water equivalent peaks, and that's because we start getting this rapid densification of the snowpack during the spring months. Again, going from about 20% here during the accumulation season, rapidly increasing to close to 40% during the melt season. Snow depth is declining during this initial phase, but we're still actually maintaining or adding mass to the snowpack during that spring series. Keep in mind, again, that these are point measurements. These are measurements that occur at a station or throughout our station network. And there's a myriad of different snow environments in between these stations that range from snow-free all through the winter to incredibly deep snow that persists late into the summer or even all year round. And capturing all of those with the station network is impossible. Once we get into the melt season, we start to think about connections of the snow melt system with the rest of the environment and the hydrologic environment. We see some increased solar absorption due to dust on snow, melting out the snowpack much faster, steepening this part of the curve and making the melt out date occur earlier. The spatial distribution of where the snow is melting in the watershed and where it existed at the beginning of the melt season, it exerts strong influence on the magnitude and timing of runoff throughout the river network. And the degree of moisture in the soil prior to the start of the accumulation season has an effect on when we see snow melt, how much of it we see in our stream network. The soil moisture deficit, or the dryness of the soils underneath the snowpack, needs to be satisfied before that system can produce a lot of water to the stream network. So it ends up being a fairly complex system that we try to measure and capture through these individual stations. So moving forward with our lens on measuring and trying to manage this incredibly valuable resource in a variable, dynamic, and changing hydroclimate, one that's superimposed on an already tight supply and demand balance in the Colorado River Basin, we need a couple of things. We need to improve our forecast reliability, that is, its robustness to changing climate, changing conditions, and where possible, to increase our snowpack. And so we're going to go through a couple of examples now that get at those needs, and we'll start with DK going through the Colorado Cloud Seeding Program.
Well, thanks, Jeff. And really, for us, the only game in town, the only way to increase water supplies in the Colorado River Basin is cloud seeding. It's the main adaptation strategy to mitigate against climate change. And we're not doing this in a vacuum. We're doing this in a cooperative way, a regional effort. That's part of what we call the Drought Contingency Plan, or planning, the DCP, that some of you may have heard. This is one of the three legs of the stool. It's a way to increase recreational opportunities, both in winter for skiing, spring for boating into the summer, and helps us with our water supplies, of course. And that's what we're really focused on here at the Colorado River District. So how does cloud seeding work? This simple schematic scratches the surface, but I think paints the picture pretty well of how we introduce some additional dust-sized particles, some nuclei, also known as aerosols. These inert chemicals are introduced into the cloud when conditions are correct. They're uplifted by airflow over the mountain block, increasing the efficiency of the cloud to produce snow. And this is key. Clouds are inherently inefficient, meaning there's a lot of water in there that doesn't fall as snow. If we can help that process by introducing some of these particles, we can increase the efficiency and we can increase our snowpack. If we drill down, you'll see in this schematic that we need several things to really be effective. And we are constantly monitoring these variables or parameters that determine when and how we seed and if we seed. And what we're looking for is what we call supercooled liquid water. That's water that is below the freezing point, but is not frozen. So that liquid water exists in the vapor. We introduce these particles again, gloms onto those, and helps the dynamics, the cloud dynamics, result in snow. We only do this when the liquid water is present and when temperatures are in the right range between between -5 degrees Celsius and -15 degrees Celsius. And when the airflow is correct, we typically look for westerly flow and northwesterly flow to be the most efficient way of enhancing our snowpack. And there's a lot more to it. We're not going to get a chance to really go too far into it, but I do want to address a few key questions that are probably on your minds today. Does it really work? Yes, the bottom line is we have numerous independent peer-reviewed studies throughout our region that show that cloud seeding can increase a storm's snowfall by up to 15%. And it's a range. Really between 0 and 15% is what these multiple studies have shown. And here is a list of some of those. These will be provided, the full references for you to review if you're interested to really
drill down and understand how these studies were performed and how they have arrived at these different yields, increased yield of snow. And that snow, of course, runs off, and some of the associated monitoring and assessment show stream flows can be increased by up to 5% in certain areas at certain times. So there's a lot to it. Again, I encourage you to look at these references when they get emailed to you. Another question that people often ask and are maybe skeptical about are these downwind impacts. Are we impacting other folks downstream? Are we taking their moisture? Are we robbing Peter to pay Paul? That's a common phrase that people use to wonder about cloud seeding. Well, again, the body of evidence, the body of scientific knowledge shows that these, what some people call extra area effects, are negligible. They're not measurable. We have multiple studies, and you can see these here that indicate that rainfall or precipitation downwind is not impacted. Again, the point here in this last bullet is not only is it not detrimental, but it can actually increase and provide benefits downwind as well as those in our target area. So that can benefit both Peter and Paul. So not one is hurt. And you may ask, well, how is this possible? It's because of that efficiency of the cloud and also because of natural impacts and the ability to measure these changes. It's very difficult to do so. And again, more details provided.
A lot here to talk about. But another key question that's often, and I think rightly asked, is it safe? Is cloud seeding safe? This has been going on for a long period of time, and folks may be surprised by how long and how widespread these practices are. But multiple independent studies have been independent studies that there are no negative impacts to the environment, and I'll explain why that is. But this statement, again, that there's no discernible environmental harmful impacts from cloud seeding from silver iodide aerosol introduced into the environment. And that's because silver iodide, which is the agent that's used, has no immediate or long-term environmental impact. It's a stable, naturally occurring inorganic material that does not interact with the environment. So because of that, it's a very safe material, and it's not only safe, but it's optimally shaped, as you can see here, in the same crystal habit, we call it, as ice. Ice forms in a hexagonal shape. So with silver iodide particles in that same shape, ice can efficiently grow, and this dust-sized material, again, results in more net snow coming out of the clouds. If you look in your medicine cabinet today, you may actually find some silver iodide in some of the products. Antiseptics often have it, and in fact, if you're a home photography hobbyist, you may also be dealing with silver iodide and be familiar with that material. So this map shows that this is, as I said, a widespread practice, in particular in the upper Colorado River Basin, Wyoming, Utah, and Colorado. And there's leaders also outside of the basin, in Idaho in particular, where a lot of research that we rely on has been done, and a very active program to help address water supplies there. And you can also see California, big player. And the other thing to point out is cloud seeding can also be used in the warm season for hail suppression and rain enhancement for dry season crops. So it's a known process and pretty well accepted throughout. And we at the Colorado River District are managing a program here in the Central Mountains. This one particular polygon, if you can see my pointer, is what we manage. This is in the Central Mountains, one of 9 permitted areas. And this map shows over 100 generators on the ground. These are those ground-based generators that are used to dispense materials only in the proper time and place to take advantage of those, what we like to call juicy storms, to really take advantage of and enhance the snowfall. So with that, it's time to hand it back over to Jeff, and he's going to talk about the next phase, which is the monitoring and assessment piece of our snowpack.
Yeah, thanks, DK. So once we arrive at our snow on the ground, whether it's enhanced by cloud seeding or not, we really need to gain a better understanding of how much snow is there to improve our ability to forecast our river runoff. And the reason we need this capacity is that our current water supply forecasting system is vulnerable to unusual conditions. Vulnerable because the methods that are used operationally rely on this year being a lot like years in the past. They compare the current amount of snow on the ground, the current conditions, to what the historic record has shown. And with the changing conditions that we're experiencing and that are projected to continue, and all of these myriad factors that influence the behavior of the snowpack and diverge it from the period of record, these methods that rely on a calibration type approach are vulnerable to inaccuracy in the future. One example of that from the American River in California, showing forecast accuracy from 1990 through 2011, shows that half the time the forecasts were on the order of 20% accurate, and in 1 in 5 years approaching 40%. In this era of converging supply and demand balance, a 40% uncertainty on a forecast is pretty untenable for most operators to accommodate. So the question rapidly turns into, what can we do to make our water supply forecasting systems more robust to these changing conditions? Well, one way, simplistically, is to decrease our reliance on that historic record and turn towards a more physical, realistic representation of the snowpack rather than these index-based methods. And one way to get there is to increase the availability and use of spatial data that covers the entire landscape rather than just point measurements sparsely distributed. We've got two things going for us in this endeavor. The first is that the snow accumulation pattern, where the snow is on the landscape, drives snowmelt volume and timing. Where the snow is important for snowmelt volume and timing. Think about it as if all of the snowpack were on a high elevation north-facing slope, it's going to melt off a lot later and a lot more slowly than if all of the snowpack was on a low elevation, warmer south-facing slope. So that distribution matters for melt volume and timing. The other factor is that solar radiation, solar energy controls snowmelt. We like to think of air temperature as driving the snowmelt, but it's actually that the air temperature also goes up in response to solar radiation. And it's really the absorption of solar or net shortwave radiation into the snowpack that drives its melt. Fortunately, these two factors, the snow distribution across the landscape and how much radiation it's going to absorb, can be monitored operationally with remote sensing from satellite and airborne platforms. And that's the background, the driving motivation behind the development of Airborne Snow Observatory, which is a set of paired remote sensing instruments on twin engine turboprop aircraft. We fly a scanning lidar or laser scanner system, as well as a spectrometer, which is a high resolution camera that sees out into the near infrared wavelengths. We use the lidars to make surface elevation maps and get snow depth, which we then convert to water equivalent. And we use the spectrometer to map the albedo or reflectivity of the snowpack, which governs how much solar energy it will absorb. I'll concentrate on the depth and water equivalent component, again, using this lidar system. LiDAR is an active remote sensing technology. It shoots a pulse of laser light and times how long it takes for that pulse to go out, hit the target, and come back. That time can then be converted to a range measurement because we know the speed of light. And this system we use sends out a pulse of light about 800,000 times per second, scanning back and forth under the aircraft as it moves across the landscape. We convert those range measurements into elevation measurements using positioning and attitude sensing systems in the aircraft. And we fly the aircraft back and forth, basically mowing the lawn over the entire river basin to achieve complete coverage. From those elevation maps, we make one snow-free and then another when the snow is covering the landscape, and we subtract those elevation maps to get snow depth at very high resolution, typically 3 meters spatial resolution on these snow depth measurements. And you can see in this image on the left, which is about a 250 or about a 500 meter square box, you can see the high variability in this particular environment with very shallow snow in the dark blues in very close proximities to some very deep wind drifts. So capturing directly that spatial variation is key because that drives the variation in water equivalent, which is what we're most interested in. The next component is snow density, which we discussed before, which interacts with snow depth to produce how much actual water is on the ground in the form of snow. We use the existing station networks, which measure depth and water equivalent, so we extract density from that, and then we run a high resolution Snowpack evolution model, ingesting those data to keep it tightly coupled with observations. We map density at 50 meter resolution across the landscape. Multiplying those two data sets together gives us a map of snow water equivalent 50 meters across the entire watershed. And it's difficult to overstate how revolutionary this perspective is. We're used to seeing maps of the distribution of the snowpack across the landscape from optical satellites. So this gives us that, of course, but those sensors can't give us the water equivalent, the actual mass of snow in the basin across the landscape. So this is a revolutionary perspective, which we've been doing repeatedly over a number of basins. So for example, in the Tuolumne River in the Central Sierra Nevada in California, we've been flying multiple times per year starting in 2013. And through that effort have captured a wide range of climatic conditions in the Sierras, with 2015 being the lowest snow year on record in California, and 2017 vying for the top accumulation year on record, and a number of years in between. So we produce these maps for each of these flights and use our snow model to interpolate between them, and we can use either the native resolution of these maps and deliver those as a data product, or at the other extreme, we can add up all the snow that's in that map to produce a single basin total water equivalent volume, and that's what the plot at the top right of this image is showing. The evolution of the total basin suite through each of these snow years. We've been doing this in partnership with the operators of Hetch Hetchy Reservoir in the Tuolumne River, which is the water and power supply for the city of San Francisco. They have deployed these data to help them in decision support across these wide range of conditions. We've developed the capacity to produce these data rapidly, so delivery of these data products within a couple of days of the flight, which makes them maximally relevant for water supply decision making. And this effort has served to bridge to adjacent basins as well, because of the successes we've achieved in the Tuolumne. The advantages of flying the full basin versus just the conventional station-based assessment of the snowpack. The main thing is that the snow monitoring stations that exist are all in fairly similar environments in a relatively narrow elevation band. They're below tree line in forest clearings where there's not much wind effect, and they're just capturing straight snowfall. Because of that, we don't sample the low and high elevation parts of the basin. And as we track the snowpack evolution at these stations through the blue line here in this plot, we can see that they're melted out by sometime in April, when we know we can see with our eyes and also with the ASO measurements that there's a lot more snow left in the basin above the elevations of those snow pillow sites. So this full basin snowpack mapping allows us to continually inventory the full snow water supply in a particular watershed. And that has direct impacts on our ability to forecast water supply in that basin. This plot shows the relationship between the ASO measurement of total basin water equivalent versus the measured inflow to Hetch Hetchy Reservoir from that flight date through the end of July. And we can see this near perfect relationship that adds a lot of confidence for decision making and operating that reservoir to meet the often conflicting operations goals of hydropower production, water supply delivery, and ecological flows. Again, these benefits persist equally from the wettest year through this driest year, so supporting both flood management and drought management. response from our water management partners in California has been tremendous. I like this quote from Wes Moynier at Turlock Irrigation District, downstream of the Hetch Hetchy operation. He's equating this new data source to having an extra reservoir in his operation. In other words, the efficiencies and optimizations that are allowed by a much tighter forecast are the equivalent of having extra supply in the basin, which is a resounding endorsement. A couple of other success stories in California. We've engaged tightly with the U.S. Bureau of Reclamation Fish Recovery Program in the San Joaquin River. Like many basins in Colorado, the San Joaquin has an annual flow that far outstrips the storage capacity on the system. Meeting ecological goals like fish recovery means delivering water at times that are different from typical agricultural demand. So trying to hit the spring and fall peaks that the fish are used to ecologically while maintaining the supply and meeting all the demands of the agricultural service in midsummer. In order to meet those goals, and there's a number of specific flow factors with specific forecast accuracy requirements that are needed to achieve this, we have worked with the Bureau of Reclamation to incorporate ASO forecast into their forecast guidance, and that has allowed them to meet these restoration flows and effectively rewater the lower San Joaquin, which had not reached the Bay Delta prior to 2014. So great ecological success story there. Next basin to the south in the Kings River, a slightly different scenario. The Kings River Water Association manages Pine Flat Dam, except when there's a flood declaration, and then the U.S. Army Corps of Engineers takes over operation of the dam and operates it completely for the sole purpose of protecting infrastructure, with no regard to any of the delivery obligations from the Water Association. In 2019, the official forecasts were coming in quite a lot lower than the ASO numbers that were mapped. The Water Association was able to use the ASO number to select the high end of the forecast range to govern operations. They were able to deliver water early and avoid a flood designation and the Army Corps operation of the dam. Through that effort, they saved 100,000 acre-feet of water last year, which equates to $100 million of water in their service area. So a massive success for them, and a factor of 100 over the cost of the program. Without the ASO guidance, they would have been stuck using the 50% exceedance from the official forecast. So we see California maturing as a snow mapping program with ASO. We've done over 300 snow on flights since 2013 in the 10 Southern Sierra basins. We're doing this on operational timescales. The future build out in California, we're looking to cover the entire snow covered portion of the state over the next 5 years. So exciting times there. We've also been flying quite a lot in Colorado. In fact, the first ASO flight ever was based out of Grand Junction, and we flew in the Uncompahgre River. We've been doing a lot of science support projects for NASA headquarters and the terrestrial hydrology program. We've participated in the state-funded forecast improvement projects in the Rio Grande Caneos basins, as well as the Upper Gunnison. And just this year, been partnering with Denver Water to fly in the Blue River. I'm going to zoom in a little bit on the Upper Gunnison operation here to give you some flavor of what these data look like. Again, this was CWCB project support for these flights in collaboration with the Upper Gunnison District, Department of Energy Watershed Function Science effort in the East River, as well as the NCAR, National Center for Atmospheric Research forecast improvement work. So here we're looking at snow depth across the Upper Gunnison. That's the East River on the left with the town of Crested Butte under my cursor there. And then over to the east is the Taylor River above Taylor Park Reservoir. Colors going from low snow in the blue up through yellow into deeper snows in the reds. And we can see a pattern that may be familiar, low snow at the lower elevations and trending upward as you increase in elevation. We also see a bit of a longitudinal gradient here with more snow in the west and a bit of a rain shadow in the east. Not unexpected, but as we zoom in, we can see that the picture of snow accumulation and redistribution across the landscape is quite a lot more complicated than just that elevation gradient. Yes, that elevation gradient is there, but we can see lots of different aspect and slope effects with lower snow amounts on the south facing and windward slopes and more snow in the sun protected and wind protected alpine cirques facing to the northeast. We can also see a very complicated pattern of wind redistribution, producing very shallow snow and very deep snow in very close proximity across the alpine areas. Zooming in on the ski area of Mount Crested Butte, just for a sense of scale, you can tell which ski runs they have snowmaking operations on with these yellow stripes indicating deeper snow. You can even see the terrain park features with the big jumps that they build by pushing snow around. So really, I think this image gives a sense of scale for not only the resolution and the accuracy of these data, but the fact that we have that resolution across the entire watershed. Jumping ahead now to 2019, which was a much bigger snow year than the very dry 2018, 7th of April. Again, Crested Butte here in the center of this oblique image. And again, a similar pattern of the elevation gradient. And we zoom in and we see that more complicated pattern and one more factor in 2019 that wasn't really present in 2018, and that's the extensive avalanche cycle that occurred throughout the month of March in 2019. We see evidence of that. There's a good one here in the center of the image where this blue area on the slope is shallow because all of that snow avalanched and ended up in these big red piles down in River Valley. And once you see that pattern, you can start seeing these avalanches all over the place throughout this extensive and destructive avalanche cycle. This is Rustler Gulch above the town of Gothic, and this whole slope has avalanched and ended up in the bottom of the valley. So we've got this pattern complicating the already complicated pattern of wind redistribution you can see the right side and lower part of the image. June 2019, so partway through the melt season, we see that there's still quite a lot of snow at the upper elevations. The blue line in this image is a contour line at 10,600 feet, which is the elevation of the highest snow station in the basin. And so we can see that our sensor network is effectively dry at this point, and there's still a ton of snow in the high peaks, demonstrating the capacity of this technology to map that terrain. Another way we can distribute or show that is through an elevation band, summing up all of the snow that's in tight elevation bands as we march up the mountain. In this plot, we see elevation across the bottom, and Snow Water Equalent is represented by each of these boxes, the April flight in the blue and the June flight in the orange, and the red triangles representing the elevations of the snow stations in the basin. We can see by June, at the middle and upper elevations, we're persisting or maybe even increasing a little bit our snowpack of those elevations, while the low elevations are melted out and our snow stations are rapidly going dry. So capturing these high elevation snow dynamics can be critical. Just over the hill into Castle and Maroon Creeks in the upper Roaring Fork, City of Aspen's water supply, we see a similar pattern last year from the April to June elevation distribution. In this case, quite a bit of snow accumulation between April and June with a lot of late season storms. You'll recognize, no doubt, the familiar profile of the Maroon bells in the image on the left, and with the snow depth map draped over them, really these deep piles of snow at the base of the cliffs, those persist late into the season and really form our water supply and stream flow late into the summer months. Backing out a little bit from the Maroon bells, which are now at the upper right, we can see a bit more of the terrain. Again, the extensive avalanching and complicated distribution of snow in the alpine cirques, as well as this sort of stippled pattern down under the forest. In the foreground is Highland Bowl at Aspen Highland Ski Area, and you can see that there's a different character of the snowpack in that managed snow terrain, one that's skied frequently and packed down compared to elsewhere in the unmanaged basin. Stepping out a bit further, we can now look at the entire Castle and Maroon systems and that full distribution of snow in all of its complexity across the entire terrain. One last example here from Colorado last year with the Blue River Denver Waters operation with Dillon Reservoir. Our June flight in particular was of great interest there. Again, at the higher elevations, the snow was persisting even as the low elevation in the valleys were melting out. People were starting to mountain bike. Our second flight in June occurred just as the snow-tell sites were melting out. It was a couple days before that, and just after an initial peak in stream flow inflow to the reservoir. At that time, we calculated 115,000 acre-feet of water in the, remaining in the system above the snow-tell sites, which in retrospect, after the year closed out, turned out to be half of their total inflow to the reservoir that year. That gave the Denver Water folks confidence to delay their operations a couple weeks, allowed them to catch the second higher streamflow peak and achieve a full pool for water supply while not flooding Silverthorne downstream, which is always an important goal. So great result with Denver Water last year. One example of how we're integrating these data with water supply forecasts, this example is from our National Water Model development partners at NCAR, but similar efforts are afoot with the River Forecast Center. This is an example of what's termed an ensemble streamflow prediction. And the ensemble is an ensemble of model runs starting from one particular snowpack state and running each of the past 30 years of weather records through the model to produce different trajectories of streamflow prediction. All of those different trajectories represent a plume of uncertainty, and the center of that plume is the forecast trace as we march into the late season. The example here from 2018 in the East River in the Upper Gunnison, we can see that the forecast plume, or the central median of that plume, the white line in the background, is under forecasting the observed inflow in the East River gauge at Almont. With one injection of the ASO map on May 24th, it brings that ESP forecast right in line with the observed streamflow at that gauge. And again, this is the value of that high elevation snowpack, in this case with the late May flight, recalibrating the model state, the model snow distribution that's uncaptured by the instrument network that's out there. So a great example of how those data can be valuable. So to summarize, we see this ASO snow mapping program as it's evolving and growing to complement the existing networks that are out there and really provide a fundamental data source to improve forecast systems and improve our snow knowledge and monitoring going forward. This is very much a research to operations effort coming out of this program developing at NASA Jet Propulsion Lab. And importantly, we're integrating with these existing networks. We use the existing ground station network to ground validate the lidar information and to provide snow density information to constrain that model. So it's really a fundamental and valuable addition to this ecosystem that represents the next generation of water resource management. Briefly, some emerging opportunities here in Colorado in the Northern Front Range and Upper Colorado. We've got the Blue River down here, which we were just talking about, and there's some great opportunities with the consortium of Front Range water providers, as well as the River District here and its constituents for the Upper Colorado main stem and Front Range basins. The Upper Gunnison work that we've done, as well as Castle Maroon for Aspen, represent kind of a keystone for the Upper Frying Pan, Roaring Fork, Arkansas, and Crystal Systems, a key component of the River District's portfolio. And down to the south, our existing work in the Uncompahgre, Rio Grande, Canales basins serves as a bridge to start looking at some of the southwestern districts' operations. So exciting times as this program builds out in Colorado. And hopefully we've been able to convey both through this program and through the cloud seeding efforts that DK is overseeing that responding to this variable changing hydroclimate that really imprints itself on the water supply and demand imbalance requires an all hands on deck kind of approach, where we're trying to improve forecast reliability and augment supplies through these efforts like cloud seeding and basin-wide snowpack inventories. So hopefully we got some time for questions.
Yeah.
We do have about 5 minutes for questions. Give us just 1 second to sort through. So the first question we have comes from a Jackie D. As far as cloud seeding goes, how does that % increase in the amount of snow falling from a storm translate to actual measurements? As in, how much extra snow can you get out of a storm by cloud seeding?
That's a great question, and one that's both easy and hard to answer. So every storm is different. every storm track and every operation of cloud seeding is different. But if we just take the Central Colorado Mountain Program that I help to manage with our operator, we've been able to look seasonally over the last, we've been doing this since 2016. Seasonally, we've been able to document an increase of between, and this may not make a whole lot of sense, but between 40,000 and 80,000 acre feet of water that wouldn't have been there absent our operations. If we were to break that into a per storm, like I think you're asking, maybe we get between, well, in a good year, 20 seedable storms. So you would take that volume, theoretically divide it by 20. So 2,000 acre feet per storm. Again, or if you want to think about it in terms of snow, maybe a little bit easier to understand. If it was a 10-inch storm and we were able to up that by 10 to 15%, that's 1 to 1.5 inches of additional snow. So hopefully that kind of gives you a range of understanding. But I do want to stress that it's very variable, and these numbers I'm giving you are based on sort of the optimal situation or a long-term average. Some storms are down to 0, some storms are greater, maybe 20 to 25% in some of the greatest impacts. So yeah, thanks for your question. And again, we'll try to capture these questions and summaries and send them out with the packet. So do we have a few more?
Got the next question is, can you review again where you're cloud seeding? Are you seeding in the Gunnison Crested Butte area? Thanks.
So yes, the short answer is cloud seeding is occurring in that area. However, that's not being managed by the Colorado River District. That's being managed by the Upper Gunnison River Water Conservancy District based in Gunnison. But the same techniques are used. And I think we can, again, provide some better information, but I would point you to Upper Gunnison if you're interested in the Crested Butte area. For us, the ski areas that we in the Central Mountains are focused on would be Winter Park, Breckenridge, Keystone, Vail. Those are sort of the heart of some of the ski areas that we're working with and seeding actively. But again, south of here, other operators and other managers are doing those activities.
Okay, I think we've got time for one last question. This comes from David Mays. If I understood correctly, we translate measured snow depth to snow water equivalent using assumed snow density. How well can we predict snow density?
Yep, good question. So it's measured and modeled snow density. So we use measurements where they're available, and that's both at the snow pillow, snow tell locations, as well as the snow course, those manual snow tube observations, as well as any other field campaign activities that we conduct in conjunction with overflights. Then we use those field and station observations to constrain the snowpack evolution model. And we do pretty well with density to within 10 or 15%. And then in the bigger picture, density represents variation in density across the landscape, represents a small portion of the total variation in water equivalent across the landscape. The bulk of that variability comes from variations in snow depth due to a lot of different factors that I was mentioning, avalanching and wind redistribution being a dominant one. So we're more or less directly capturing the snow depth using the Airborne mapping system. That captures the bulk of the variation, which reduces the impact of that 10 to 15% uncertainty in density.
And with that, that's our time. We appreciate you again for spending your lunch with us in the Colorado River District. If you had a question and it wasn't answered, we will make sure to get those questions answered and sent out to everyone within the next couple of days. Enjoy the rest of your afternoon. Thanks for attending.